Students struggle a lot with optimization problems. So let's take a look at this one. The hardest part about them for most students is setting them up. So here's a problem that says on the same side of a straight river are two towers. So here's Tower 1 and Tower 2. Townspeople want to build a pumping station at point S. The pumping station is to be at the river's edge. Here's the river, with the pipes extending straight to the towns. Set up a function and its domain. That's what we're doing, just setting it up. That would show you where the pumping station would be located to minimize the total length of the pipe. Now this picture gives us all the details that we need. They give you that this X distance is the distance the pumping station is from the first town, perpendicular to the first town. This whole distance, the distance between the towns along the river, is 4 miles. So that means that this distance from S to this point where town 2 is going to be 4 minus X. Now, I'm just setting up a function in its domain that shows you where the pumping station should be located to minimize total length of pipe. So that means I'm minimizing this length here, which I'm going to call little c, and I'm minimizing this length here, which I'm going to call capital C. So if I start with little c, I see a triangle right here. So I'm going to blow up that triangle down here a little bit. So make it bigger. This is little c, this is x, and this is 1. Now that's a right triangle, so I know that the sides of the legs squared, the sum of the legs squared, is going to equal the square of the hypotenuse. So that means c squared equals x squared plus 1. C is equal to the square root of x squared plus 1. Reason why I don't put plus and minus, because little c is representing a length. So that's the distance from town 1 to S in terms of that length there, X. Now if I look at this guy, let me blow it up a little bit. Just taking a look at this guy, I have 4 miles here, I have 4 minus X here, and I have capital C here. Now this is another right triangle, okay? It's another one. And I know that the hypotenuse squared is going to be the square of the legs, sum of the square of the legs. So I'm just going to multiply this out. So c squared is equal to 16 minus 8x plus x squared plus 16. So c squared turns out to be x squared minus 8x plus 32. So that tells me that c is equal to the square root, capital C, x squared minus 8x plus 32. All right. So now I have both distances in terms of x. So if I consider my function that I'm going to minimize, so this is total distance, let's say, so total as a function of x is going to be little c plus big C. So the length of little c plus the length of big C is the total sum of the pipe in terms of x. To minimize that function will give you the minimum pipe that is needed. So this is going to be x squared plus 1 plus the square root of x squared minus 8x plus 32. Now it also says we need to give the domain for x. So the domain for x, take a look at this one. So if x is 0, I put the pumping station S over here, so that's the smallest x can be. And if I put the pumping station at the other side of the extreme here, that means x is equal to 4. So my domain, in the end, is going to be x goes from 0 to 4. And that's the setup of that problem. Right now, we're not worried about solving it, just worried about setting it up.